Good morning.
Good morning.
Good morning.
Good morning, Shaki.
Good morning.
Good morning, Tatiana. Okay, ladies. Now, before I start, any questions about chapter 15? Nope. Okay, goals. So what we said yesterday was we can say, okay, pixel size is inversely proportional to pixel density. And we can make it that pixel size or pixel density will lead to or determine, yes, okay, what we end up calling the spatial resolution. Just for a reminder, we could say the greater the pixel size, lesser pixel resolution, or lesser pixel density. Lesser pixel density, poor spatial resolution. Clear? On the other hand, we can say that, okay, yes, if we have a smaller pixel size, we will have a greater pixel density. And if you have a greater pixel density, yes, okay, that will lead to a good spatial resolution. Then we had another, and we could see as, okay, number of bits per pixel. we can say it's okay. That will determine what is going to be. We can say it's okay, the grayscale. And the grayscale will determine the contrast, which also is okay, indirectly or inversely will determine, yes, okay, what we call the contrast resolution. Now, what we mainly can say that, okay, yes, if we had a great number of pixels, a great number of bits per pixels, that was going to give us a grayscale. If we had a great grayscale, that will lead to, yes, okay, a lesser contrast. And the lesser the contrast between the shades of gray, that will lead to, yes, okay, we can say it's okay, a good contrast resolution. Whereas, okay, it's on the opposite side, if we had less number of pixels, or bits per pixel, sorry, that will lead to, yes, okay, a small grayscale. The smaller the grayscale, yes, okay, the greater will be, yes, okay, the contrast between the shades of gray. And that will lead to a poor contrast resolution. Is that clear? Okay, so you can mainly say, okay, and all this is okay, is going to be, it's okay, the pixel density. That means, okay, will determine whether we have a good or bad spatial resolution. We can say it's okay. It's mainly going to be, it's okay, the number of bits per pixel that will determine, yes, okay, whether we have a good or bad contrast resolution. Is that clear? Okay. Let's see, new sheet. And I'm going to go with this one here. Well, can you guys see this new picture here?
Yes.
Good. Okay. So although that's okay, I showed it to you guys, that's okay, the other day when we were talking compression. Right. Okay. But that's okay. As an example, we can mainly see that, okay, or you can mainly say it's okay that we actually is okay have two different grayscales. Right. Okay. Okay, where one is okay, there's a total of okay, that's 1, 2, 3, 4, 5, 6, 7, 8, 11 sheets. Whereas okay, the other one there's only is okay, a total of 7 sheets. Right, okay. Yeah, okay, that's in either of and on both of the scales, that's okay. What we have on one side is white, white, black, black. Okay. Well, you can mainly say that okay, as when we go from yes, okay, white to black, or from black to white, the difference between the shades is lesser in this scale here, which we can just label as A versus B. Okay, well, okay, at the difference means that's okay, all of a sudden there's like a duck, 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 duck. Yes, okay, there's a great difference between yes, okay, the shade compared to yes, okay, what you have here. Okay. Did that make sense? So if this, for instance, okay, what the varieties of shades of gray that we had, that could be used in a picture. That will mainly mean that, okay, yes, For instance, okay, a shade like this one here is missing. Even as okay, you can see it's okay. This shade here is missing. You can see it's okay. Even this shade here is missing. Right, okay. Not to talk that okay, as even this shade of gray here is okay, is not what you find in your yes, okay, gray map down here. Did that make sense? So what that will mainly mean is that okay, yes, any reflection which was producing, yes, okay, or which could have been, yes, okay, displayed using any of these shades of gray here, had we used this gray map, will not be shown as the specific shades of gray if you chose this one here. Okay, because it's okay, these two shades here maybe it's okay displayed at this shade here. Whereas you can say it's okay, these two shades here may be displayed like this. Did that make sense? So yes, okay, now mainly as okay, call that okay as this shade here cannot be specifically as okay displayed on your image. Or this one here. Okay, so both of these shades, which could be as okay, or shades which mean as okay were produced by okay as different kind of tissues, will be shown by one common shade. Likewise, as okay, these two here will be shown by this. Did that make sense? We can even say it's okay that these two shades here, that's okay, may just be shown by this. And so on. Okay. Yeah, okay, now why would those okay tissues have different, yes, okay, shades of reflection? Maybe because okay, they may be as okay, relatively stronger or weaker, relatively stronger or weaker, relatively stronger or weaker. But if they are shown by okay, just one shade or one common shade, that's going to okay, call that okay, as you will have end up having a, you can say it's okay, poor contrast resolution. Did that make sense? Did that make sense, girls?
Yes.
Okay, now please keep in mind, go that it is not only in grays and black and whites, for instance, okay, that you have contrast. Okay, any color out there has okay, yes, we can say it's okay, different varieties of it. Let's say you want to just okay paint a room in your house. Right, okay, you may go to, let's say it's okay, Home Depot or any store where you can buy us okay paint and say, well, okay, I want to paint my yes okay room blue. Okay, you just tell them, well, okay, I want to paint my room blue. Now they may ask you, okay, or they may as okay show you as okay a whole array, a whole big variety of okay as blue colors that they are going to be able to make. Those are all going to be as okay, you can say as okay, different contrasts of blue. Did that make sense? Did that make sense? Whereas okay, on one side, yes, okay, or yes, okay, that blue scale, if you want to put it that way, there's going to be as okay, a blue color, which is super duper light. Okay, so light blue that it actually is okay, it just looks like white. Whereas okay, on the other side, you may have okay, as whereas okay, as on the other side, you may have okay as a very, very dark blue. Now then maybe you can say, okay, 1001 varieties of blue to choose from. Okay, which you mainly can say is okay, where you go from is okay, the lighter side to the darker side, or from the darker side to the lighter side. Across those varieties of blue, you may as okay will find okay as a lesser difference between them, because okay, 2 or 3 or 4 neighboring blues may as okay at the first look alike. Okay, so that lesser difference will mean that okay, as you have a lower contrast. Did that make sense? Okay, but there's a greater variety. Now, if you find that okay, go and say, oh, this was too much. Let me go to a place where okay, as the choices are limited. You may go to another store where they sell paint, and okay, yes, say, well, okay, I'm looking for some blue paint. And they will say, okay, listen, dear, we have skylight or skylight or sky blue. We have okay, navy blue, and we have okay as regular blue. That's the 3 choices we have. That will be as okay a lower blue scale, if you want to put it that way, right? Okay. Now, when you go and say, okay, there's skylight, there's blue, regular blue, and then there is navy blue, there's going to be okay, a great difference between the two. Or between, yes, okay, the blues as you go from the lighter side to the darker side, or vice versa. That mainly is okay, we can say okay, there's going to be a greater contrast. Did that make sense? Okay. There's going to be okay, a greater contrast. Now, if you say, well, okay, I'm not going to buy blues to paint my room. I'm going to just okay, buy blues, just okay, use them in a painting. Okay, that's where you may say, okay, I want to have okay, as a greater varieties of blue. So like okay, something that is very light blue should be painted as very light blue. Something which is slightly darker is going to be painted slightly darker. Okay, but if the varieties of blue that you have is only 3, okay, something that falls as okay, that actually would have been as okay between the very light blue and we can say a regular blue, should either be painted as okay, as light blue or regular blue. Mainly because you didn't have any okay shades in between those 2 varieties of blue. So yes, okay, your painting or that you paint is going to be as okay with a poor contrast resolution, because you're not going to be able to as accurately as okay show the contrasts of as okay any specific reflections. Okay, so please, the lower your grayscale, the greater the contrast, the poorer your contrast resolution. Yeah, we actually said that, okay, yes, because that's okay, that the poorest contrast resolution, that was when we had the greatest contrast. And when was it that we had the greatest contrast? Was when we had the smallest grayscale. When did we have, yes, okay, the smallest grayscale? That was when we only had 1 bit per pixel, which we actually okay, will say would be what was bistable. Yeah, that was mainly okay, just 2 shades. Or we can say okay, 2 colors, black and white. Okay. Now, one thing that okay, yes, you will be asked about, and yes, we guess okay, go yes, okay, the review questions and the question at the back of the chapter. You will see that okay, yes, they will be asking you questions about yes, okay, how to calculate the number of bits per pixel. No, sorry, the number of, you can say it's okay, the shades of gray on your grayscale. Okay. And please keep in mind, though, that that's going to be as okay shades of gray that can be put into a pixel. Now the formula is mainly going to be as okay that we can say, okay, now it says 2 raised to the power n. Right, okay. The n here mainly as okay stands for as okay the number of bits. Okay, to be more specific, as okay, it's going to be the number of bits as okay per pixel. Okay, now the lowest number of bits that we can have in a pixel was 1. So 2 raised to the power 1 mainly means 2 multiplied by 1, which becomes 2. So that's why it says, okay, the lowest number of bits per pixel was 1, which was going to okay, give you 2 shades, which will mean it's okay going to be overcalled bistable. Did that make sense? Okay. Now, if you said 2, and okay, the number of bits was 2. Now, please keep in mind, guys, it is not going to be as okay. It may going to be as okay 2 multiplied by itself like this. So here it's okay, we have 4 bits. No, sorry, 4 yes, okay, sheets. If each pixel had 2 bits. So we actually okay, we'll be able to just okay have up to 4 shades of gray. Whereas okay, if you go 2 raised to the power 3, and that mainly mean that okay, as 3 here actually that's okay, it's going to be as okay the number of bits. That mainly now mean that you go 2 multiplied by 2 multiplied by 2, which becomes 2 times 2 is 4 times 2 is 8. So you actually have okay as 8 sheets if we go on to yes, okay. Yeah, if we go on to the next one says okay 2n, where we mean is okay, just to say that okay, as n here is going to be 4. We can actually write that as 2 raised to the power 4, which mainly will mean that 2 is going to be as okay multiplied by itself 4 times. Then you can say it's okay, 2 times 2 is 4 times 2 is 8 times 2 is 16. Did that make sense? So you can say it's okay, just from taking as okay, if from 3 pixels or 3 bits to 4 bits, it goes from as okay 8 shades to 16. Not to talk about as okay, if we go and say as okay 2 raised to the power 5. Which means this will mean now that okay, I should go and say as okay 2 times. Yeah. we actually become 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 32. So 2 raised to the power 5 can actually, that's okay, show you up to 32 shades of gray on your image. Did that make sense? Okay. So that's okay. This raised to the power 4 here, this raised to the power 3 here, this raised to the power 5 here. Doesn't mean that you go and say it's okay, 2 multiplied by 5. Because that would mean that that's a give you 10. That is not really, that's mathematically it's okay, incorrect. Okay. Likewise, it's okay, 2 raised to the power. Oh, sorry, 2 raised to the power 4, for instance, that's okay. It doesn't mean 2 times 4. Because then you mean it's okay, just like God, that's 8 sheets. That is wrong. 2 raised to the power 4 means 2 multiplied by 2, multiplied by 2, multiplied by 2. Or you multiply 2 by itself 4 times. So for 3. Did that make sense? So if you have, let's say, it's okay, it's okay, 5 bits per pixel. That would mean that that pixel can actually, it's okay, store up to, it's okay, 32 different shades of gray. Whereas, okay, yes, if you had 4 bits per pixel, that can store up to 16 pixels or 16 shades of gray per pixel. Right, okay. Now, some of you may then ask, okay, yes, how many bits would we need to, yes, okay, let's say, yes, okay, display, yes, okay, up to 25 shades of gray. Now, 4 bits, that's going to be, yes, okay, too low because the maximum that it can display is 16. So for 25 shades of gray per pixel, yes, okay, you will need 5 bits. 32 is mean, yes, okay, it's just the maximum. Is that clear? Is that clear, girls?
Yes.
Okay. And you can go on, you can say that's okay, 2 raised to the power, let's say 6. Okay, so how many will that be? That would mean it's okay, that'll be, they say 6, not 2 multiplied. Yeah. Okay. 6. Where we already know that, okay, for the first 5 is going to be as okay, 32. So 32 multiplied by 2 becomes 64. And so on. Okay, ladies. So any questions about contrast and contrast resolution? Any questions about grayscale and contrast, or grayscale and contrast resolution?
No.
Okay, ladies. Are you guys good on analog to digital and digital to analog?
Are you talking about like what we talked about yesterday, like the graph, like the converting from analog to digital, digital to analog?
Mhm.
Yes.
Okay. Okay, girls. Then I guess we can just go on to okay. So please, please, please make sure that you know that this is how we get okay. Calculate the number of gray sheets per pixel. Where okay, as here n is what should be okay, the number of bits. Okay. Now, ladies, we can talk as okay, pre-processing. And we can also as okay talk post-processing. Now, what I said the other day is that okay, as pre-processing is, we can say okay, any processing of data before, and that's mainly as okay, why we call it pre. It is stored in the memory. Whereas, okay, it's on the opposite side, post-processing is going to, we can say it's okay, any processing of data. Okay. After, and that's mainly it's okay, why we call it post. It was stored in the memory. Now, for instance, okay, if we look again, it's okay at our figure 17 point, well, 15.7, sorry, where we mainly said there's the transducer. Now, please keep in mind, guys, although it's okay, it is not shown in your diagram, but that's okay. We can mainly says okay that okay as the receiver will be somewhere here in this whole table. But then we had okay as the E to D scan converter. And then we had what would be this, okay, the memory. So what we really can say is, okay, that all this processing that the signal undergoes before being stored in the memory would be examples of pre-processing. Is that clear? Well, okay, after that, we could mainly says, okay, what will mainly happen? Well, two things could happen. Either what the data go back to, yes, okay, to what we could call, yes, okay, E to A scan converter. And then it's okay. But that was only going to be, it's okay if we had an, let's say it's okay, analog display. That makes sense. Whereas if we didn't have an analog display, but rather had we can say it's okay, a digital display. The information is okay, what had gone straight from the memory is okay to the digital display. But whichever path it takes, whether it is this or whether it is this, all this here, whichever path is going to be as okay post-processing. Is that clear?
Yes.
Now, pre-processing. Pre-processing is okay. Practically is okay, as they say, is okay. Can't. Oh, sorry. Can't be reversed. Which mainly means that, okay, as the processing is okay, once it is stored in the memory, well, okay, it's done. Well, okay, you can't really undo it. Clear? Whereas post-processing, because what I mean is that's going to be as okay, we can say it's okay, just we can say it's okay, processing, or yes, okay, maybe altering or changing on the data that already is stored. Well, okay, yes, that can be reversed. Okay. Clear? That can be reversed. You actually is okay, can undo it. You can undo the processing or post-processing. Or you can then, okay, as save the processed image as a new image. But if you don't want to, yes, okay, you can go back and say, well, okay, I just made some changes, but I don't want to save it. Okay, that's fine. Okay. But it's okay, the changes that the adjustments that you do to the system as a part of pre-processing is not going to be reversible because it's automatically okay, going to get saved in the memories. Is that clear? Okay, it's going to get more clear. Hopefully, it's okay once we start talking about it's okay the different kinds of magnifications. Now, girls, in your book, on yes, okay, page 249, you may see a table that says okay 15.6. Okay, that says 15.6, which means okay, we can okay mainly lists. We can say okay different processes that are considered to be pre-processing. And different processes that are going to be considered post-processing. Okay. Now, some of these terms, yes, okay, we already, yes, okay, may have talked about. Some of them are going to, yes, okay, be discussed later on in the chapter. But when they say that, okay, yes, for instance, okay, your time gain compensation was an example of, okay, as pre-processing. Now, if you look back here, I say, yes, okay, listen. In the whole course of it, okay, how the signal actually is okay is traveling. It goes to it okay from the transducer to the receiver, then and okay, it goes to the analog to digital scan converter. And maybe because okay, your time gain compensation or compensation, as a matter of fact, yes, okay, is a function of your receiver. That's why it's okay, it falls under it's okay being an example of pre-processing. Did that make sense? Okay, where you actually just okay could adjust your compensation before it's okay that data went on to it's okay to the scan converter, and ultimately it's okay was saved in the memory. Did that make sense? Did that make sense? Now they say it's okay, log compression. Don't worry about the log. Log compression is mainly it's okay, just what we call compression. And again, it's okay, a receiver function. And as I said, yes, okay, receiver functions are going to be as okay part of pre-processing. Because any processing of the image, okay, data before it was stored in the memory was what we called pre-processing. Is that clear? Next is what they call as okay, right magnification. Now, what magnification mainly will mean is that okay, yes, that we enlarge the image. Or we can say it's okay, that actually it's okay, we want to just okay, zoom in on a region of the image, maybe it's okay to take a closer look on it. Okay. As a matter of fact, ladies, that's okay. There are going to be as okay two kinds of magnification. One is wide magnification, the other one, the opposite of that is going to be read magnification. Where read magnification is still magnification, that is okay, we enlarge the image. What we call a read magnification, mainly because that's going to be okay, what will be considered as a kind of magnification, which is post-processing. Very mainly says, okay, we actually is okay, are enlarging, are taking a closer look at primary as okay, what we'll call is okay, a region of interest on the image. By image that already is okay, has been stored in the memory. Whereas wide magnification is before it has been stored in the memory. Is that clear? Now, the next thing that you see, and okay, we haven't discussed that yet, but it's called persistence. Well, okay, here they use the term persistence. You girls can mainly, it's okay, just already write it and says, okay, that's going to be, it's okay, what we will call temporal compounding. Okay, and we will talk about temporal compounding later on in this chapter here. Okay, so that's okay. Another name for this, okay, temporal compounding is going to be persistence. And that's going to be, as okay, an example of pre-processing. Just like we had temporal compounding as a pre-processing, or as an example of pre-processing. Likewise, we also have okay, something that we call spatial compounding. Which again is okay, going to be as okay, an example of yes, okay, pre-processing. Where if you look at temporal compounding, it's like going to just go compounding, it's okay, pertaining to time. Spatial compounding pertaining to space. Okay, and both of these fellows here, okay, are going to be brought up later on in this chapter here. There is something that they call, yes, okay, edge enhancement. Now, yes, okay, although yes, okay, being yes, okay, mentioned later on in the chapter, but we're not going to really, yes, okay, talk about it. And then, okay, as the last one is going to be as okay, where will be as okay, fill in interpolation. And that's something that we as okay, definitely yes, okay, will talk about. But what we mainly can just okay, what all these processes here are examples of pre-processing. Okay. Processing of the data before it has been stored in the memory as an image. Now in pre-processing, well, the first option that okay, the first example that they give is any change after a freeze frame. We can mainly say, okay, let's put it this way, sorry. Oh, let's word it this way. That's going to make it more, that's okay, clear. Then we can say, okay, that will be as okay. Changes of an image. That is frozen. Which mainly as okay is going to be as okay one way by which we actually will be able to as okay do what we call read magnification. Which mainly as okay just will bring us back to yes, okay, then what about write magnification? That's going to be as okay on an unfrozen image. So you can mainly say, okay, it's okay, one of the main differences. Technically, it's okay, that will determine are you doing a write magnification, or read magnification is, did you froze the image or did you not froze the image? Or was the image being magnified as you were scanning? Or are you as okay magnifying on an image that already is okay has been stored in the memory? And you mean as okay, you can say it's okay, retrieved it from the archive and magnified it. Is that clear? But we will talk more about that when we go and talk about the specific two kinds of magnifications. We can say it's okay, black and white inversion. Right. Okay. Now some of you say it's okay. What would that do? Now let's say that okay, you have an image. Let's say it's okay that let's say this part here of the image, for instance, okay, primarily as okay was black. And we can say okay, this part of the image here was white. There is okay, black and white inversion. Mainly will be that okay, this image, once you invert it, that's okay. What was black is now going to be white. And what was now white is now going to be black. Is that clear? Okay. But your image actually is okay. Well, okay, you actually it's okay. Be notified that okay, yes, it is inverted. So there actually that's okay is a function knob or button that we can press, and actually it's okay will invert your image. Now this okay for regular SOK B mode, we'll call that black and white inversion. But again, you can say it's okay, then what about this? Okay, the shades of gray. You can say it's okay, the dark shades of gray will be shown as light shades of gray, and white light shades of gray will be showing as dark shades of gray. Is that clear? Is that clear, girls?
Yes.
Okay, just excuse me for a second. Okay, girls, I'll be right back. Okay, ladies, sorry, welcome back. Okay, now some of you may ask, okay, as what is going to be as okay the benefit of that? And okay, because the main benefit is that okay, as if there is something in the dark area that you would like to see, you can actually just okay make the dark area light, and practically as okay will become more clearly visible. Okay. Now, since that's okay, right now we only as okay, up to this point here is okay. Mainly we already had talked about as okay, black and white images. Okay, where you can have okay as where we said okay as okay, black and white inversion. But just keep in mind, go that okay as later on in a later chapter, we will talk about, for instance, okay, what would be Doppler? Okay, and when we say Doppler, that's okay, that's going to be a kind of Doppler, which will be as okay, color Doppler. Where you actually as okay, will also be as okay, able to, you can say as okay, invert your color Doppler maps. Okay, now that is not going to be mentioned in the chapter 19 where we talk about color Doppler. That inversion is going to be as okay, an example of post-processing. But practically it's okay if you match the dots. You can actually say yes, okay, that okay as color Doppler inversion is also as okay an example of post-processing. Because what we mainly have in color Dopplers means okay, there's going to be colors instead of okay at different shades of gray. Although it's okay, those colors will tell us something else. Okay, but it's okay, since we can invert the colors on the color map. Likewise, okay, like here, okay, it's gray map where we have black and white, and okay, then different shades of gray. But you can mainly say, okay, what was black becomes white, what was white becomes black. And lighter grays become darker grays become lighter grays. And oh, yes, okay, an example, yes, okay, what I find, yes, okay, a color, or yes, okay, black and white inverted image may look like. Do any of you have older pictures in your house? Pictures that were developed from a negative. Yes, ladies.
No.
Huh?
No.
I think so, but I'm not sure.
You probably will. Now, if you look at those negatives and compare it to the picture, you will mainly see that, okay, as whatever is, you can say it's okay, dark on the picture will appear light on the negative, and vice versa. So you can mainly say, okay, your negatives is a black and white inversion of the positives, which will be the actual picture. Is that clear? That's pretty much okay as what black and white inversion means. Where the inversion practically means that's okay upside down. Right? That it flips. So that's okay. That inversion from black to white or from white to black actually is what we can call as okay black and white inversion, which is going to be as okay an example of post-processing. Okay, because that's going to be done on an image that already as okay was, you can say as okay stored in the memory. Is that clear? So processing on any image that was already as okay stored in the memory is going to be as okay what we call post-processing. Then I made that's okay, just mention yes, okay, read magnification, yes, okay, when we discussed or briefly mentioned, write magnification. And that's means okay, these two kind of magnification that's going to be as okay our upcoming discussion. Okay. But when we say read magnification, it's going to be as okay a type of, or it's going to be a kind of post processing. Because we actually is okay are magnifying an image that already is okay was stored in the memory. Okay. That we either retrieved and then magnified it. Or yes, okay, even if you, for instance, okay, we're actively scanning, yes, okay, that we have frozen our image. Even that was going to be as okay, what we can call yes, okay, a read magnification. Did that make did that make sense? Now we can mainly say as okay, the last one is okay as 3D rendering. Now, ladies, if you remember from chapter 14, when we did chapter 14, and we talked about as okay 3D imaging. Right? I mainly told you, ladies, at that time that okay, yes, the process of creating yes, okay, a 3D image. That process, for instance, okay, was what we call rendering. So even if it just had said rendering, and okay, had omitted yes, okay, the term 3D, it would still have mean that okay, as we created a 3D image. Is that clear? So if you are being asked that okay, yes, just give me yes, okay, the term rendering, and asked if this is an example of pre-processing or post-processing, it will still be post-processing. Okay. You can't say, well, okay, the word 3D was not mentioned. Well, okay, the word rendering automatically means that, okay, yes, just the process by which, okay, 3D images are produced. And how are that going to be post-processing? Mainly because, okay, what we also briefly mentioned was, okay, as to create 3D images, what the system would need is two-dimensional or 2D images, which were going to be rendered to make the 3-dimensional image. Where did the system get these 2D images from? The memory. So since it uses these two-dimensional images and render them, and these two-dimensional images were achieved or retrieved from the memory. So what did I say about post-processing? Any processing of data after the data was stored in the memory was going to be considered post-processing. So it's we'll briefly mention it's in chapter 14. Go and look at as your 3D imaging. One of the last paragraph over here is your 3D rendering or 3D imaging. Says it's by process of rendering, which is an example of post-processing. Did that make sense? So some of these terms, that's or some of these examples here, that's especially that's the ones that are pre-processing is we'll talk about them as they're being brought up in this chapter later on. And hopefully it's at that time it's it will make more sense why we consider them to be as examples of pre-processing. Now, does anybody have any questions? Nope. Okay, go. Okay, well, so just take a short break. Let me see. We can be back at, should we say 10:30, okay? Okay. Here goes. Any questions?
No.
Magnification. Written magnified so you can read it. Yeah. So what does magnification mean? It just means enlarging. Clear? Now we can say, there may be just, different ways of enlarging. We can say, you have an image which was this small. Maybe we can say it's 1 inch by 1 inch. or 2" by 2". What you mainly require is okay, a passport photo, right? Because that's going to be the size of picture that okay, can be used in a passport form. But if you like the passport or if you like the picture that you took for your passport, you can actually, it's okay. If you want to, it's okay, you can enlarge it and print it out as okay, as a 4 by 5 inches and put that in a frame or in a photo album. Did that make sense? So what you actually did was okay, you increase the size of the picture, or you can actually okay, you magnified it or you enlarged it. Okay, but in ultrasound, yes, okay, this is not going to be the kind of enlargement because you can mean says okay, the size of the image on your screen is going to remain the same. Okay. The size on the image is going on the screen is going to remain the same. You can say it's okay, it may be as okay. That's okay. 5" by 5", for instance. Just for example. Clear? Now the whole thing is okay as why is it that we, for instance, okay, would like to yes, okay, magnify an image. Or actually it's okay, enlarge it. Although it's okay, we can't increase the physical size of the image from 5" to 10", from 10" to 15". Right, okay. So, but the whole purpose of you can say is okay, magnification or enlargement is that okay, as if on the image there is something that we can see, or we may see as okay as a small dot or as okay lesion or whatsoever, and we actually is okay want to is okay take a closer look at this. That's when we will magnify the image. And okay, what your book actually is okay, may refer this dot here to be as okay is called as okay, the region of interest. Or the main is okay, just abbreviated as ROI. Okay, but any as okay, bigger or smaller as okay structure that you may see on your image. Okay, which will be as okay, which they may as okay catch your attention, or actually as okay be what we can call as okay a region of interest, because oops, what is this? Oops, what is this? Oops, what is this? Oops, what is this? So that is okay, a tag, or that means okay, you can say it's okay, catches your attention. Or you can say, okay, I need to just okay, take a closer look of that. So that becomes just okay, what to me you become interested. What is this dot here? Okay, not yet okay, take a closer look on this dot, or for instance, this dot. That's where you actually just okay, well, magnify the image. Where you actually says, okay, what first was a dot, now it's okay, when you magnify it, you can say, okay, this whole region here, mean is okay, becomes just okay, occupies just okay, the whole size of your image, which is still, you can say it's okay, 5" by 5". But that dot which previously as okay, appeared as a small dot on your image, actually is okay, now becomes big. So that is all that's okay that happens as a result of magnification. Is that clear? Is that clear?
Yes.
Okay. So pretty much, okay, as just, yes, okay, take a closer look on, okay, as anything that becomes, okay, as considered as, okay, as a region of interest. Or as, okay, would need, as, okay, a closer look. Because, okay, initially, as, okay, may just be as, okay, a dot. Now, when you magnify it, you may actually see that, okay, as what previously, okay, just appeared as dot actually is, okay, is a membrane. Or we can say it's, okay, a membrane structure. And what we actually have inside that, maybe you can say it's okay, that maybe it's okay, that's the accumulation of some fluid, which was not visible here. Okay. Not to talk about, yes, okay, this dot here, which is even smaller, but that's okay when you magnify that. It's okay, now this here is okay, maybe my region of interest. You can still, it's okay, magnify it, and okay, yes, it still becomes that 5, for instance, 5 by 5 inches image visibly on your screen. And okay, what was okay previously a little dot, yes, okay, now will be shown as okay as a bigger circle. Okay. You may realize, okay, now you can even see it's okay, what first, yes, okay, appeared as a dot. And you might have thought, okay, well, that is going to be as okay in the shape of a circle. But when you magnify, you actually realize that okay, as it has a irregular shape like this, for instance. Did that make sense? So that's all because, yes, okay, you magnified it. Now, ladies, on your console, or we can say it's okay, your keyboard of your ultrasound system, you actually, that's okay, may find a knob that says zoom. Is that clear? And that is actually going to be as okay, the knob that you will use to magnify the image. All right, it says, okay, magnify the region of interest in your image to take a closer look on it. And you mainly will see it's okay, when you turn this knob here clockwise, you actually are going to see it's okay, cause more and more magnification of the image. That actually sort of become more and more and more enlarged. Not your whole image, but mainly as okay, the region of interest. The area within the picture that you actually is okay, want to focus on. Or just as you may do, yes, okay, when taking pictures, you zoom in on the region of interest. Or you zoom in on, okay, yes, the specific thing in the picture that you are in the field that you want to take a picture of. Or if you already have the picture taken, you can still zoom in on it. And look at that, yes, okay, look at that area within the picture and take a closer look at it. Mainly, yes, okay, by magnifying it. Or as we will say, it's okay, zoom into that region. Clear? Where, okay, as if you just turn it counterclockwise. Once you have zoomed in, that's means it's okay. How you actually is okay. Well, you can say it's okay, unzoom. Or it's okay, you can say it's reverse the magnification. Okay. That you say, well, okay, yes, this was our image to begin with. let's say that, okay, yes, this here is, okay, was our region of interest. Now, when we first zoom in on it, our image may, yes, okay, go from this to this. We further zoom in on it, it may go like this. We further zoom in on this, it goes like this. And that may mean that, okay, as we further zoom in, it goes from this frame to this frame, this frame to this frame, this frame to this frame, to yes, okay, be displayed on your image. And okay, what first appear as, okay, as a small dot circle, actually is, okay, when it is zoomed in, it's going to be, it's okay like this. But that was mainly, it's okay when we went from it's okay in the blue direction. When you say, okay, well, okay, yes, we looked at this, we studied that, okay, what that dot was. Now we need to, yes, okay, unzoom, and that's means, okay, where you mean is, okay, just go from this image, large image, to this frame, to this frame, to this frame, until, yes, okay, it is unzoomed. And what you actually, yes, okay, end up seeing again is, okay, as the same as it was when you started. Did that make sense? Did that make sense, girls?
Yes.
Okay. Now, as far as magnification is concerned, we in our previous, okay, before the break, yes, okay, mentioned that we had two kinds of magnification. Right, okay. One was what we called, and I know that your book says it oppositely, but I would just write it like this and say, okay, one was what we call right magnification. Other one was what we called, or referred to as being read magnification. Is that clear? Now, as far as your right magnification is concerned, right magnification is going to be, as okay, be an example of pre-processing. Whereas, okay, as your right magnification was an example of post-processing. Did you girls get that? Now, what we also said that pre-processing was, which now is okay, as okay, applied to right magnification, because right magnification is an example of pre-processing, is that there was not reversible. Or as it may also, as okay, be mentioned as, okay, yes, it's going to be as okay, irreversible. Whereas post-process, whereas read magnification, which was an example of, okay, yes, post-processing. And what we said post-processing was is going to just okay be reversible. Now goes when we okay specifically okay talks of wide magnification and re-magnification. Now, wide magnification is going to okay mainly be performed, or we can say okay, be magnification of an image, which is unfrozen. Image. Or as we can say, because it was an example of okay as pre-processing. Not stored, or you can say it's okay saved in the memory. So whenever we actually is okay doing what we can call wide magnification, this is when we is okay magnify on an image which is not frozen. Or we can say it's okay unfrozen, that okay as unfrozen image that okay as that the frames are not frozen. Whereas okay as when we go read magnification, mainly because okay it is post-processing. Or when we did, and we said about it, okay, read magnification, or post-processing was frozen frame. So read magnification can be done on a frozen image. An image where the frame actually is captured or frozen. Or mainly because okay, it is a part type of okay, or remagnification is an example of post-processing. We can say okay, based on that, that will be as okay that the image is saved. Most likely saved where as okay in the memory and or in your archive. If you girls get that. So as far as magnification is concerned, it's okay, what make or what determines whether you are right magnifying or read magnifying is, did you freeze your image before you magnify it? Or did you not freeze the image before magnifying it? Clear? But post was okay, read magnification, it can also be done on an image which is okay, or is okay, we can say it's okay, saved in the memory. A previous scan of the patient, a scan that was done, let's say it's okay, a couple of weeks ago or a couple of months ago, but it is saved in the memory. And you can actually just okay, retrieve it from the memory and say, okay, oops, let's look at this dot, let's look at this region of interest or whatsoever. Let's take a closer look at that. That kind of magnification is going to be read magnification. Is there anybody who has any questions yet? Now, ladies, just a little cheat, because okay, usually people get confused or forget which of the two magnifications is read, or sorry, it's pre-processing, and which of them are post-processing. Just remember, girls, you first write, and then read. Is that clear? So before something can be read, it has to be written. So first come writing, then come reading. Did that make sense? Right, okay. So if I say, well, okay, here, read what's written on the slide. Well, okay, there's nothing written. Did that make sense? So first comes writing, then comes reading. First is pre, then is post. Did you ladies get that? Okay, go. Let's just look at, okay, how right magnification works. Now, what we mainly said was, okay, that was going to be as okay, practically as okay on an unfrozen image. Okay. So yes, okay, ladies, what we actually yes, okay, also have on our console or keyboard. It's usually yes, okay, down here at this level. It says, okay, you have okay your regular keyboard with A, B, C's, X, Y, Z, so on, so here. Because it's okay, this was your depth. And we have okay as the different modes. Most likely as okay, your computer or okay, your keyboard will have a mouse here. This knob here is okay, there will be a knob that says zoom. But then this knob here is okay, say freeze. And if you press this knob here, it's okay, and it turns green. That means that your image is frozen. Whereas, okay, if it is not green, that means that, okay, yes, your images are not frozen. Which means that, okay, what you see currently is actually, okay, what you're scanning at the actual time. Did that make sense? So if you enlarge the image as you are scanning, that will be a right magnification. Because you didn't froze the image. Okay. Now what we can say is, let's just take this as okay, into as okay, photography. Okay. Now let's say that, okay, as you are sitting in, let's say, stadium, watching, yes, okay, a baseball game. Or any game, it doesn't really matter. And there are people, yes, okay, sitting at the other end of the stadium on the benches. We can say it's okay. Hundreds of people. Did that make sense? Now, for instance, ladies, that's okay. If you took a picture of all these people here, like that, well, okay, you didn't really zoom in. It's okay. Everybody's singing there, it's okay. The opposite side. At the opposite side of the stadium, it's okay. I took, it's okay, a picture where it's going to be, it's okay, hundreds of people in the picture. Whereas if somebody comes and tells you, well, listen, dear, some celebrity, whosoever he or she is sitting in a crowd on the opposite side of the stadium. You may say, it's okay, that celebrity is okay, maybe it's okay. You can say it's okay. You are become, yes, okay, your region of interest. Just like, okay, as we said, that, okay, yes, on our images, okay, we had that little dot, which means it's okay because I have been here. Right, okay. Now you haven't taken the picture yet. And that's when you say, okay, let's zoom in on this area here, because that's where it's okay, the region of interest is. That's where it's okay, where the celebrity was sitting. That may mean that, okay, as the whole image size that you will get will be this, and you get, okay, as instead of seeing it's okay, the celebrity, or it's okay, the region of interest just as a single dot, you actually, it's okay, get a picture of that person. And say, yes, okay, he was sitting in the crowd. Now, when you zoom in like this, and then click, that would be, yes, okay, an example of, okay, as wide magnification. And now you actually can see that, okay, as this image here, that is what is going to, yes, okay, go and, okay, yes, get stored in the memory. And when you can say, okay, once this image here, for instance, okay, is taken, then you can't untake it. Did that make sense? Did that make sense, dears?
Yes.
So you actually, as okay, you can say as okay, zooming in on the region of interest. Which is going to be as okay, unfrozen because as okay, you haven't taken as okay the picture yet. That will be as okay, right magnification. Now, what we mainly will say here is okay, this image of the person is okay here that will have okay as a good spatial resolution. Mainly because okay, the pixel density of okay as this zoomed in image or taken after yes okay you zoomed in is actually as okay equal to yes okay what the original image would have been. Because they are made up of, but we says okay, that we actually said okay, as each pixel was means okay, just meaning a pulse. Yeah. Now, on the other hand, ladies, if we said read magnification. Now that's going to be yes, okay, we can say it's okay, relatively it's okay, easier for me to yes, okay, demonstrate. Here is okay on a Zoom session. Because okay, what we mean said about yes, okay, read magnification, yes, okay. Either that will okay done on a frozen image. And what we mainly can say is okay, that okay, as then an image is frozen. Because it's okay, it automatically becomes saved in the memory. So the kind of magnification that we'll be doing on this frozen image or is okay, or a saved image will become yes, okay, read magnification. Because read magnification, as you said, was an example of. Hola, go. Post-process. Now we can also say as okay, either as okay, we froze the image, or it was an image that was okay, as already saved in the memory and always as okay in the patient's archive or record that can be retrieved and again it's okay magnified. Okay, so what I mainly as okay just did was okay, I chose a picture here. Can you guys see this picture?
Yes.
Right, okay, I retrieved that, yes, okay, from my, yes, okay, so this is a picture which, yes, okay, now actually it's like already is stored on my computer. You can say, it's okay, this was a picture of, let's say, it's okay, a scan of a person's whatsoever organ, tissue, structure, organ. Did you ladies get that? Now, right now, yes, okay, what you actually will see is that, well, okay, yes, it has, okay, a pretty, yes, okay, good spatial resolution, right? Okay. You actually will be able to see, okay, that there's two hands, that's okay, brought together. Within that hand, that's okay, there's this lady sitting. We can actually, that's okay, clearly, that's okay, see all the details very well. So that's okay. In this case, we can actually say that we have, okay, as a good spatial resolution. Did that make sense? Now, what I will be doing is, yes, okay, I'll be magnifying this picture here. Let's just, okay, as mark a region of interest. And say, as okay, let's say that, okay, as this hand here, for instance, is our region of interest, which we actually just, okay, would like to, as okay, magnify and take a closer look at. Did that make sense? Just to choose any area, right? Okay, we say, okay, this hand here is okay, that's going to be as okay, a region of interest. So now as okay, I will magnify this picture here. Meaning that's okay too. So this is a magnified one. We may magnify it even further. We may magnify it even further, further. Okay, now she moved off. Okay, so we can actually just okay, just bring it in. Can you go see this? So this is actually as okay, now her hand being, we can say it's okay, zoomed in. Or we can say, okay, we zoomed in on the region of interest. But this is going to be as okay, an example of read magnification. Why? Because okay, this was an image that was okay, as retrieved from the memory or storage of my computer. Is that clear? Is that clear, girls?
Yes.
Good. Now, I don't know whether you girls can send, but that's okay. Let me just, okay, yes, make a dot. You see this black dot that I just made here? That is actually just, okay, 1 pixel. I can just make another one so you just see it. Oh, sorry, that probably smushed it out. This again, yes, okay, is 1 pixel. Okay, so yes, okay, when the picture was unzoomed, or because that's okay, when we first started, you actually, that's okay, couldn't see the individual pixels. Did that make sense? That we actually, that's okay, will see now that okay, yes, in read magnification, the number of pixels in the zoomed in image is the same as they were in the original picture. But mainly because, okay, we zoomed in, yes, okay, the pixels becomes larger. So pixel size increase, which actually call as okay, that okay, as the spatial resolution will be degraded. Or if you just look at her mouth here, you can see as okay, the mouth is pretty much okay, zigzag, right? If you say okay, that the mouth was okay as our region of interest, you can actually okay, see the individual pixels of the mouth, which okay, has made disappear or become yes, okay, the pixel size actually becomes lesser as we zoom out. If that makes sense, girls. Okay, so that's okay. We can say it's okay. The main disadvantage the main disadvantage of read magnification is that the spatial resolution may degrade. Why? Because of the increasing sizes of the pixel. Did that make sense? Whereas in write magnification, that was not an issue. That was not an issue. The image that you get as a result of just, okay, write magnification has the same pixel density or pixel size as it had in the original image, which was okay as before you had zoomed in on the region of interest. Did that make sense? Okay, so what we mainly as okay could say was okay. That this image here, had I, for instance, yes, okay, taken this image like this, clicked it, and saved it, and said, and somebody later on told me, yes, okay, did you know that such and such and such celebrity also, yes, okay, was sitting and watching, it's okay, the baseball game, football game, whatever game. And I then go and okay, zoom in. Or actually, that's okay, do what we just did with the picture. When I zoom in, yes, okay, I may, yes, okay, be able to, yes, okay, zoom in, yes, okay, yes, okay, he was sitting right here. But since, okay, that is zooming in on an image that already is, okay, has been saved. That's going to cause, okay, yes, the pixel density, yes, okay, in the zoomed in image actually is going to, yes, okay, get reduced because the size of the pixels will become bigger. So due to, yes, okay, the increase in pixel size, the pixel density becomes less in a red magnified image. Whereas if I zoomed in on the region of interest and then took, yes, okay, the picture, yes, okay, I will have, okay, yes, a picture where, okay, yes, where this zoomed in image here is going to have, it's okay, we can say it's okay, the same pixel density as this whole image here, which I made on later on to zoom in. And okay, yes, call that okay as the pixel size becomes bigger. Okay. But in read magnification, that's okay. I can say, okay, well, okay, we zoomed in, we looked at a structure. If you want to save that zoomed in image, you can. If not, well, okay, you don't have to. So it's okay, it will not automatically, it's okay, be saved in your memory. Because okay, it already was frozen. And how do you freeze an image or unfreeze an image? You can mainly say that, okay, yes, that there was, okay, yes, a knob on your keyboard down here that says freeze. Activating that mean yes, okay, mean that, okay, yes, you froze on the image in time. Okay. Now the thing about it here that freezing an image is that, okay, even if your transducer moves, the image is already frozen. Nothing is going to happen to it. Besides, okay, if you combine, okay, you can say magnifying it, but it's okay, it is. You can say it's okay, already saved. And now you're magnifying on it. Whereas in read magnification, that's okay, since you don't freeze the image. If you move your transducer, well, okay, yes, you may now say, yes, okay, that the region or area that you're scanning is also going to, yes, okay, change. And you may lose, yes, okay, the view of, okay, yes, your region of interest. So we can say, yes, okay, practically, yes, okay, the best way of, okay, as magnifying is to be as okay to read magnify. Because, okay, then you freeze your image and say, okay, I know where my region of interest is. Okay, you can even check, yes, okay, the transducer off. And okay, then just focus on, okay, as magnifying. Is that clear? But the main negative point about is, okay, read magnification or either, okay, as if you magnify, yes, okay, too much, that actually is, okay, will lead to, is, okay, reduced pixel density, which means, okay, will lead to, is, okay, because it's, okay, relatively, is, okay, poor spatial resolution. Did you ladies get that? So we can say as, okay, zooming in on a region of interest or any area that you want to, yes, okay, capture before, yes, okay, the picture is taken or, yes, okay, image is taken, that will be read magnification. Whereas, okay, as zooming in on an image that already has been taken, or we can say it's frozen in time, will be as, okay, read magnification. And I show you, yes, okay, the effect of, okay, as read magnification, yes, okay, on your spatial resolution. Any question, ladies? Okay, girls, now just take a lunch break, and okay, yes, we'll be back around, should we see us, okay, 12:15 for review, final review for your midterm, which is tomorrow, okay? Okay. Hey, girls, welcome back. Now, any questions? Any point, any topic, any relationship? Or the first 14 chapters that you feel that needs to get, okay, yes, further clarified, explained, or discussed. Yes, ladies. It's now or never. Yes, ladies.
There, I have a question.
ahead.
The dynamic receive focusing, that cannot be adjusted by the sonographer, only by the machine, right? It's determined by the machine, right?
Yeah. But don't worry much about the dynamic. Well, you can say, okay, receiver focusing.
Okay.
Okay.
I have a question.
Go ahead, Joe.
What happens with a vector array if it has a damaged PZT?
It's not mentioned, so Hakuna Matata it.
Okay, thank you.
No problem. But we can probably say it's okay, most likely because but it's a mixture of what you want to call it. Just okay, your mixture. It's a combination of your linear phased array and linear sequential array. So it probably is okay, can have the same as okay, it says an erratic effect on the image. But since it's not mentioned, then okay, yes, you can't be asked about it. Okay. Anything else?
One more question.
Yeah, go ahead. Dave.
Is there an equation for frame rate or just for T frame?
Frame rate. No, you can mean it says okay. The equation is that it's going to be as okay reciprocal to your T frame. So if your chi frame, for instance, okay, let's say the cycle was, let's say, okay, 1 millisecond. Okay. That will mainly mean that yes, okay, you will have a frame rate of 1 kilohertz. Did that make sense?
Yeah, thank you.
The main thing that you need to know is that, okay, as both of these two here, yes, okay, were inversely proportional, not just inversely proportional, just like, okay, yes, frequency and period. Just like PRF and PRP were inversely proportional and reciprocal. So you say, okay, if the period for one frame is going to be 1 millisecond, it actually will mean this 1 millisecond actually means 1,000 of a second. That will mainly mean that, okay, as in 1 second, you will have, yes, okay, 1,000 frames. So you can maybe say, okay, put it this way and say that you actually have, yes, 1,000 frames per second. Yes, okay. That frames per second actually is okay, becomes the frequency. Frequency of what? The frames. Did that make sense? So the only thing that's going to, yes, okay, be different between frequency, pulse repetition frequency, and frame rate is that, okay, it's maybe, okay, just you can say it's okay, different events that occurs in a specific period of time. Likewise, when you compare, yes, okay, period to pulse repetition period to chi frame, it's just, okay, the time that it takes an event to complete. When we say plane period, that was okay as 1 cycle. When we say it's okay, PRP, we mean yes, okay, meant that's okay, the time between yes, okay, 1 pulse to the other pulse. Where we say it's okay, T frame, the time it takes the system to yes, okay, create 1 frame. Okay, did that make sense? But mainly, yes, okay, my dear, as you scan, unless you freeze the image, your system is continuously producing frames. It says, okay, that if the period was 1 millisecond, that means it's like in 1,000 of a second. That's the time that it takes the period to, or as okay, we can say it's okay, 1 frame to be completed. Which may mean that, okay, then you will have 1,000 frames in a second, which becomes your frame rate. Did that make sense?
Yeah, it did.
Okay, so the main thing about it, okay, yes, okay, yes, if you're given yes, okay, any T frame or any frame rate, whichever, you just have just okay, it's going to be the reciprocal of that number. That will become yes, okay, you were. If you're given a frame rate, the reciprocal of that number is going to be yes, okay, be your T frame. But you mainly says okay, if your frame rate was 1,000, the reciprocal of that is going to be as okay, 1 over 1,000 second, which mainly will be the same as saying it's okay, 1 millisecond. Because you take a second and divide it into 1,000 equal halves, each half or each, okay, 1,000 equal parts, sorry. Okay. Each part is going to just be 1,000 of a second, or the same as 1 millisecond. Anything else, my dear?
Yeah, so we went over the equations on, the questions on 133 a couple days ago, but I still don't get it.
133. You said page 133, right?
Yeah, page 133.
Okay, let me see what they are about. Not a couple of days ago, we did them as recently as yesterday. Oh, no, probably not. Okay, let's look. And now any questions specifically is okay that you have a problem with.
I just don't understand how we get the answer. Like I was trying to write out the relationships, but it's still I just don't get it.
Okay, let's see. So yes, okay, the questions, yes, okay, here that we have a bunch, yes, okay, that's okay, related to the diagram that we have. And we mainly will say, yes, okay, now this dimension here, that's going to be 12 millimeter. So they come in says, okay, that means, okay, going to be, yes, okay, your diameter of your PZT. 12 millimeters wide. And we can say, okay, also, yes, okay, 12 millimeters tall. The next thing that they have given us is, okay, yes, we have a beam. Like this. The next thing that they say is that, okay, yes, the focal depth is 8 centimeters. And then they give us up here a depth of, also, okay, a distance of 4 centimeters. And this here actually represents as, okay, what we call the focal zone. So this is your focal depth. And okay, that's what we were in orange is, we can say it's okay, the PCT dimensions. Did that make sense, my dear?
Yeah.
Good. Now the first question reads, what is the best estimate of the diameter or width of the sound beam as it exits the transducer? But the main is okay, say it's okay, if you look at the beam right here, what will be as okay the best estimate of its transducer? Now here we can say as okay, my idea is going to be as okay the very same as the width of the transducer, which are going to be as okay 10 millimeters or 12 millimeters. Because the beam just has okay, it's emitted the transducer. It hasn't started to converge that. Says okay, it's going to start off with a diameter of 12 millimeters. Did that make sense?
Yeah.
Good. Now the next question that they ask us is okay, what is the diameter of the sound beam at a depth of 8 centimeters? Now, what do we see that 8 centimeters represent? The focal depth. So at a depth of 8 centimeters, that is actually is okay, going to be as okay, your focus. And what did we say that okay, as was going to be as okay, the diameter of the beam at the focus? Half of what over here. So here's okay, the width of the beam would be half of 12 millimeter, which is 6 millimeters. And since that's okay, here we talk about is okay, round or circular PCT is okay, the height will also have been 6 millimeters. Did that make sense?
Yeah, I get it now. I was like trying to divide 8, so I was confused as to why it wasn't 4.
No. Your 8 centimeters, my dear, that's the depth at which the beam focuses. Right. But then yes, okay, just ask us, okay, yes, and the next question is, well, okay, yes, what is going to be the diameter of the beam at a depth of 16 centimeters, which will be here, for instance. Now we can say, okay, for the first 8 centimeters, the beam converged from as okay, a diameter of 12 millimeters down to half, which is going to be 6 millimeters. Whereas in this instance here is okay, it's going to is okay for the next 8 centimeters. Because it means that okay, this will be another 8 centimeters. And then here's okay, means okay, we just diverge out to again become have a diameter which is going to be 12 millimeters as well. Because that's okay, the first 10 centimeters was okay to the focus, where it narrows. For the next 8 centimeter, we're going to be okay, where it diverges to an equal diameter, which okay is where we add this to this becomes just okay 16 centimeters. Okay, so what is the diameter of the sound beam at a depth of 16 centimeters? 8 plus 8 is 16. Did that make sense? The
Yeah.
next question that they ask you is, okay, at what depth is the focus? It's as green as it can be. Because at the end of your focal depth, that's going to be as okay at which the point will focus at. They go as okay, what depth indicates or mark, okay, what depth marks the beginning of the focal zone? Now this area here is okay, that was your focal zone. Now what did we say about the focal zone, my dear? Okay, well, okay, here is okay, the total distance of your focal zone is 4 centimeters. But practically, as okay, what we mainly will say is that okay, as half of it falls into the near zone, the other half falls into the far zone. So the depth of which okay, your focal zone is going to be starting as at a depth of 6 centimeters, because you may as okay just go 2 centimeters back from the focal point, which was at a depth of 8 centimeters. Whereas if they ask, okay, where is going to be, it's okay, the end of the focal zone, you can say it's okay, 8 centimeters, but then, okay, yes, another 2 centimeters, so 8 plus 2, that becomes a depth of 10 centimeters. So that's going to be, it's okay, the end of the focal zone. You got that?
Yeah, thank you.
Okay. Any other questions, dear?
Not for me, no.
Anybody else? Anybody else? Jesus. Anybody want to say anything?
I have a question.
Go ahead, check.
So on page 489, last night-
489.
yes, in the back of the book, the exam review.
Okay, 489. 489.
Question 311.
Okay.
And it says a PCT crystal in the shape of a disc provide a continuous ultrasound wave, and the beam is on focus. So for 311, if the diameter of the sound beam is 8 millimeters at the depth equal to twice the near zone length, and the PCT has a diameter of 16 millimeters. I know that's false. I know that, and I know the reason why. But isn't that the same? Wouldn't that be like the same case if it was a post ultrasound wave, because the diameter will be still 8 in the near. Okay.
Yeah.
Okay. So what will basically, so it didn't matter that it's continuous. It would be the same thing if it was post.
Yeah.
Okay.
It's not a matter of the continuous. Okay. Okay.
Then going back to hold on, the focusing. You guys were just there. Hold on. Never mind. I was going to ask you a question about it, and I know the answer now.
Okay.
But if you can we go over the sound beam divergence again?
Sound beam divergence.
Yes, that's on page 139.
Questions or just the relationships?
The relationships. So because I'm looking at the figure 9.7. So I see, so the smaller the diameter, the bigger the divergence.
Mhm.
The larger the diameter, it looks like
Because we can say,
the
okay,
beam.
now we says, okay, divergence of beam first of all is okay, where does this occur? In the far zone. What did we mean by the divergence? The spreading out. Okay. Now, just like, okay, your focal depth is going to be as okay related to two things. The diameter of the PCT and we can say, okay, the frequency of the transducer. But here is okay, your beam divergence is actually going to be as okay, inversely related. Inversely related to both of these. Did that make sense? Where we mainly says, okay, since they are inversely related, that if a transducer had a bigger PCT, if a transducer had a bigger PCT, that would have led to, yes, okay, a lesser divergence of the beam in the far zone because they are inversely related. Or vice versa. If the PCT was smaller in size, that will lead to greater divergence of the beam. Did that make sense?
Yes.
Clear? And or if a transducer is okay had a lower frequency, that will also lead to, yes, okay, greater divergence of the beam. Whereas if you on the other hand say that okay, as a high frequency transducer will lead to, yes, okay, lesser divergence of the beam. And where was it that this divergence here happened? That was in the far zone. So we can mainly as okay, just say that okay, as if we had a transducer. Now, yes, okay, just to first relate to, yes, okay, the PCT size, for instance. Then we say, yes, okay, we have a small PCT versus, yes, okay, we can say, it's okay, great PCT. Wow. Now here we just going to just, okay, look away for the fact that they also have, okay, different focal depths. Okay, because the main thing that we just want is okay, yes, okay, how is this PCT size here going to, yes, okay, be related to the divergence of the beam, which means okay, it happens in the far zone. So we can say, okay, this means okay, we have our far zone begins. Now we had a smaller PCT. That is going to cause greater divergence. So for us, okay, for this smaller PCT is okay, what will happen here is that there will be a great degree of divergence. Whereas, okay, we said a bigger PCT, that will actually cause lesser divergence, which means, of course, okay, the beam will be diverging like this. Did that make sense?
Yes.
But the same relationships may also as okay apply to the frequencies. So again, as okay, we can say as okay, if we had a beam or if we had a transducer, that we may as okay, just are going to say as okay, that transducer is okay, that may have, for instance, okay, if you had a high frequency. Or as okay, maybe as okay, a low frequency. How is that going to as okay determine as okay the divergence of the beam and the far zone? So you remain to say that okay, yes. Now we're just going to say, okay, disregard that, okay, as different frequencies may also cause, okay, the focal depth to be changed. Okay, because right now we're just focusing on, okay, what happens in the far zone. So for us, okay, for the, we can say it's okay, the high frequency beam, or sorry, low frequency beam. Okay. That's going to be as okay, a greater divergence. So again, that low frequency beam will have a greater divergence in the far zone. Whereas, okay, as the high frequency beam has a lower divergence in the far zone. Did that make sense? Did you get that here?
Yes.
Okay. And what we made is, okay, you can see is, okay, would be ideal for us, okay, diagnostic imaging. Ideal for diagnostic imaging is going to be as, okay, we get, okay, as a lesser divergence in the far zone. Why? Because this lesser divergence actually is, okay, we'll call it, okay, as we will have a better, first of all, yes, okay, either lateral resolution and or even, yes, okay, elevational resolution in the far zone. Because as, okay, the beam is, okay, remains as, okay, at a narrower diameter in a far zone if it diverges less compared to, yes, okay, if it diverges a lot. So that's where we again can say as, okay, that high frequency transducer causes less divergence of the beam in the far zone, which is, okay, mean it will lead to, as, okay, better, or you can say, okay, relatively, as, okay, improved lateral elevation resolution in the far zone compared to, as, okay, low frequency transducer because it will diverge more. Okay, so the more the beam diverges, that's okay, more likely is it that you will end up with a poor elevational resolution and or lateral resolution. Because the more the beam diverges, the greater becomes the diameter. The greater the diameter, the greater the numerical value of these two resolutions here. And the greater the numerical value, the poorer the resolution. Did you catch that?
Yes.
Any further question?
Can we brush up on A mode, the amplitude in chapter 11?
A mode?
Yes. I thought I knew, but reading over the chapter and my notes, I'm just like, maybe I don't know as
Okay.
much.
Listen. A mode, first of all, yes, okay, we'll need to know, yes, okay, what does A stand for? And that is amplitude. Clear? Second thing was that, okay, yes, in all modes, whether it's A mode, B mode, or M mode, what did we have? We had two axes. So the two axes in A mode were the y-axis which will listen. And the other axis was x-axis, which was this one. Now, my dear, the reason that we call A mode and A mode, the A is okay, stood for amplitude, is that we can actually say, okay, that the strength of the reflection actually is okay, is going to be shown in an amplitude of a wave. And that is going to be as okay displayed along the y-axis. So the y-axis actually is okay indicates as okay or marks the amplitude. You can say it's okay amplitude of reflection, which means as okay the strength of the reflection. And what is the strength related to? You can mean it as okay the amount of energy that is going to be reflected. But it's not going to be shown as brightness, as if it had been in B mode. But actually it's okay with a bigger or smaller amplitude of a wave. Whereas, okay, as along what your x-axis indicates is the depth. Now, for both of these axes here, we can say, as okay, this point here is the 0 point. So as we go up here, that will mean as okay, as we may get a wave that is going to as okay be bigger or bigger or bigger or bigger. Which means it will mean that okay, as that wave is produced by a reflection of a greater or whatever strength. So the size of the wave actually is okay, or the amplitude of the wave actually which is going to tell us the amplitude or the intensity or the strength or the power of that reflection. Whereas okay, as we go along the x-axis, this is at a 0 depth. This may be as okay, a greater depth, even 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 greater depth, like that. But we can say, okay, if it stops here, we can say, okay, this will be as okay, the max depth. Or here's okay, that will be as okay, minimum depth. Likewise, okay, so if you go along the y-axis, because okay, this will be as okay, minimum intensity of amplitude. Where okay, we can say, okay, this will be as okay, the maximum. So if we have a wave that okay has an amplitude like this, sorry. That means that okay, as a reflector at this depth produce the reflection which okay is such a great strength. But that strength is not going to be applied as okay shown as a bright or dark shade, as it would have been in B mode, but rather as okay by a bigger spike or smaller spike. So we can actually say that okay, as the size of the spikes, or as okay, waves at different depths. Mainly as okay, we indicate as okay the strength of those reflections. Which mainly going to be as okay, strength is going to be as okay, how much energy is being reflected. Did that make sense?
Yes.
So your y-axis in this case here, which is the green axis, that's okay, mainly as okay, will indicate the amplitude. Where we can say it's okay, strong Even stronger, very strong. And then you look at these as okay, just small waves with small amplitudes. Because okay, they were relatively weak. Yeah, you can say, okay, this reflection at a shallow depth, this at a greater 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 depth. These as okay, greater depths, this at a greater depth. Because as we go along the y-axis like this, the depth increases. You could say, okay, 1 millimeter, 2 millimeter, 3 millimeter, 4 millimeter, 5 millimeters, 7, 8, 9, 10, or 7 millimeters or centimeter, whatever unit of distance that we are measuring in. Did that make sense?
Yes.
Good. So that was just okay, your A as an apple mode.
So the upward spikes is the intensity.
Yeah, but it's probably going to be better just okay, just refer to as the amplitude,
Okay.
because that's what the A stands for.
Okay.
Because when I say it's okay, amplitude, even of a sound wave. Okay, I say okay, I mean that's okay, I was demonstrating that's okay, how big the wave was, or how small the wave was. Which you can mean that's okay, it's going to be related upon that's okay, the amount of energy that it carries, which will be its strength, which we in terms of okay, as could I call power, which also as okay, then will be as okay, directly related to your intensity. Did that make sense? But maybe that's okay because your image information, or you can say it's okay, your image is not going to as okay be as okay a picture of the structure that you're scanning with different shades of black, white, and grays, but rather as okay strong amplitudes, or it's okay waves with different amplitudes, which are of different sizes. So the amplitude mainly is okay, just telling us okay how much energy are these waves here carrying. Because this will be the max energy, this will be less, and there will be the least. Because okay, this was physically bigger, this was smaller, this was the smallest. Is that clear?
Yes.
Okay. So practically it's okay. Now, if you want to look at it, you can actually say it's okay that in this scan here is okay. This would be as okay the point where it's okay your transducer is. Where you can say it's okay, this depth here is okay, there's going to be as okay greater and greater depth. Okay. How is it that the system will know that okay, as an intense as okay, a reflection with such intensity return back from such a depth? Because the time between is okay, the pulse being sent out and returning back is being calculated. How? By 13 microseconds. Let's say, okay, it took, let's say that's okay, 26 microseconds for this reflection here to return back. I would say it's okay that it will be as okay, this here is at a depth of 2 centimeters. That's for an instance. So I will display as okay this reflection here at a depth of 2 centimeters, yes, okay, on your grid or scale. Yes, girls. Anything else?
I have a question. So for M mode, do we have to know it appears as a group of horizontal waves? For M mode,
Yes.
do we have to know that it appears as a group as horizontal waves? Wavy lines, I mean, wavy lines.
My dear, in your M mode. First M was motion. Yeah. But when we say it's okay, your M mode, okay, we had 2 axes. We had the y-axis. Here's okay, y-axis, that is going to be the depth. And of course, we have the x-axis, which is time. We say time because it's okay, time of recording, if you want to put it that way. Or where is okay, actually it's okay. In this case, it's okay. This is where your transducer will be. So we can actually, it's okay, when we look at the x-axis or when we look at the y-axis, this is going to be as okay, minimum depth. This is going to be as okay at a maximum depth. Clear? And mainly that's okay, just as we go in terms of time, that's okay. The depth between the transducer and okay, yes, the moving structure changes. So if you say, okay, for instance, okay, okay, let's just say that this was point A. Here it will show it at a greater depth because there was a greater time between it's okay, the pulse being sent out and it's returning back. So it's okay at point A, it's okay, what did we have? We had a greater PRP. Or you can say a greater go and return time. Contrary as okay, if you go to, let's say, okay, something like point B, like here. It may as okay be able to show it up here because of a lower PRP or go and return time. In that point of time, where the beam was going because it hits and then comes back. So, that makes sense.
Yes.
Okay. But mainly it's okay because it's okay, it is something that is moving. That we want to is okay. Look, that's why it's okay. To record M mode is okay, it means it's okay, it just uses 1 pulse. Is going to be used to as okay, record your BM mode. Which mainly is okay, is going to be as okay, constantly firing at one spot. Like that. But say as okay, things changes in that spot constantly. that change is going to just, okay, be recorded over a span of time and shown on a graph. Did that make sense? So what we talked about is, okay, in chapter 13, greater pulses, a greater number of pulses where it's okay, reduce your temporal resolution. Or we can say it's okay, decrease your temporal resolution. You can say it's okay, the effect of that, okay, as in this instance here is okay, that you might actually, it's okay, be missing information of your guy. You can say it's okay, this would have been missing, this could 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 have been missing, something like that. So your graph, instead of okay being continuous like this, would have been broken. Okay. Mainly because it's okay, you are missing what happened. Why? Because of okay, it's a greater number of pulses. So that's why it's okay, once it's okay, turn on M mode, it's automatically going to just okay, just use one pulse to record the motion. Now, if you want, just okay, shift the area of the structure at which okay, the motion is going to be recorded. Yes, okay, you can always move this pulse this way. Or you can also move it this way. Because okay, the transducer is still, my dear, going to be as okay, producing as okay a beam. Which okay, of course, as okay, will have different pulses. But it's okay, by moving, it's okay, the pulse that's going to is okay, determine or is okay, record the movement. So okay, right now I don't want this pulse here to be recording. I want it to be this pulse. Or if you move it over here, you can say, okay, I want this pulse to be the one that records the movement. Where okay, you actually physically is okay, have the structure here. So first that's okay, for me is okay, recording the movement in this plane. But it's okay, if we move it over, it says okay, we're recording the movement in this plane. Or if you move it over here, it's okay, we are recording the movement of the structure in this plane here. While these other remaining pulses is okay, still do their job. You will still have okay as a regular okay, B mode image as well. Being produced from all the pulses, but yes, okay, that single pulse that is going to be as okay used to record the movement can be moved from here to over here to over here to over here to over here. But the number of pulses that are going to record the movement will be 1. Because you increase that number of pulses from 1 to 2, 2 to 3, 3 to 4. That will increase the T frame, which will decrease the frame rate. And that decrease of frame rate will lead to a poor temporal resolution. Anything else?
Receiving, focusing,
Permit?
receive,
Hakuna
focusing.
Matata.
Okay.
What do we need to know about the ALAR principle? Just what it stands.
Yeah. And how do you achieve it? Scooby-Doo, what do we do if an image is too bright? What will be is okay, you can say so the best way to
Adjust our output power.
reduce the brightness to make the image just right now bright. And at the same time, also as okay, we can say, okay, reduce the patient's exposure, reduce the power output. Whereas, okay, if an image is too dark, there could be two reasons for that. Either your amplification is too low or your power output is too low. But then you can say, well, okay, I can always just, okay, increase the brightness and make the image brighter. Without, yes, okay, exposing the patient to more ultrasound energy. But again, yes, okay, it's all a matter of, okay, as tuning, because too much amplification may, yes, okay, also produce too much noise. So if you start seeing noise on the image, you say, okay, that's too much amplification. Maybe to begin with, okay, the power output was too low. Because just put it in this way, my dear. The more power you transmit, well, okay, as you can say, okay, the stronger will be your reflections. You can say the stronger will be, as okay, the intensity of your reflections. Which mainly will mean that, okay, they will require, okay, lesser amplification. Because each tissue is going to has, okay, specific, yes, okay, intensity reflection coefficient. Or maybe it's okay. A fixed percentage of the energy that is going to be bombarded with is going to be, okay, get reflected back. Clear? You can increase that intensity, or you can increase that energy, you can decrease that energy, all by increasing or decreasing, yes, okay, your power output.
I have one more question.
Okay.
So I know that when we do the intensity transmission coefficient plus the intensity reflection coefficient, it's 100%. But then I was reading in the book and it says like incident intensity divided by reflected intensity is intensity reflected coefficient. Do we need to know those ones too?
Well, okay, it's just a matter of, okay, yes, the percentage. Okay, I know which equation you're talking about. No, not necessarily. Because you can mean it's okay, just say that, okay, yes, if you look at it in this way. That, okay, yes. The difference between, yes, okay, the intensity of the incidence and intensity of reflection. The difference of those will be as, okay, intensity of the transmission. Whereas if you says, okay, the intensity of the incidence and its difference from, yes, okay, the intensity of transmission is going to be equal to, yes, okay, the intensity of reflection. Yeah. So the only difference between is okay, these as plane intensities and okay as the coefficients is that okay, yes, your intensity of the incidence will be considered 100%. So then it is 100% subtract, oh, that's okay. 2% subtracted from 100% is going to be as okay, 98%. But okay, you can say okay, 70% subtracted from 100% is going to be as okay, a total of 30%. That's pretty much all you need to know. Okay, but please, as okay, when they talk coefficients, is always going to be as okay in percentages. Yeah, whereas okay, if they talk about as okay, plane intensities, not coefficient. The unit is always going to be as okay, any unit of power or unit of area. Where you can say it's okay, milliwatts per centimeter square. You can say it's okay, watt per kilometer square, for instance. Or even as okay, watt per centimeter square. You can even say it's okay, kilowatt per centimeter square. It doesn't really matter. As long as it's a unit of power by a unit of area, it will be an intensity. But that's only as okay when we talk about as okay, plane intensities. Coefficients is always going to be as okay, at least for as okay, your intensities is going to as okay be in percentages. Okay, but you still will say it's okay that okay, this in fact is okay percentage here. And so this percentage here has to add up to become 100%. Likewise, we said okay, 2% plus 89%, 98% is okay. When you add them up, what do you get? 100%. Clear? Whereas if they talk of plane intensity, they may say, well, okay, yes, 20 watts per centimeter square. Okay. 1 watt per centimeter square is reflected. Now, what is going to be as okay, the intensity of the transmission? Okay, my dear, that is going to be as okay, 90 watts per centimeter square. Because your game will say, okay, that these two here is okay, will have up to add, or will add up to become this. Did you get that, my dear?
Yeah, I did. Thank you.
Okay, so just watch out as okay what they're asking for and what are the data they're given. Because okay, they can give you as okay plane intensities. As okay, this was the incidence intensity, this was the reflection intensity. But what's going to be as okay, the reflection coefficient intensity. No, you can do it in two ways. You can calculate okay, if this was okay as the amount of, okay, as energy that was reflected out of 20 milliwatts or 20 watts per centimeter square. Then what is it? Okay, as what was the reflection coefficient? I may is okay, just subtract that reflection coefficient from 100, and it will tell you, okay, what the transmission coefficient was going to be. Okay. So in this instance here, you can mean it says, okay, if you had, okay, 20 milliwatts per centimeter square was the intensity of the incidence. The intensity of reflection was 1 milliwatt per centimeter square. That actually is okay, just makes an intensity reflection coefficient of 0.5%. Which means to me that, okay, your reflection coefficient would have been 99.5. 99.5% or 99.5%. Because this 0.5% and 99.5 adds up to become 100%. Did you get that, my dear?
Yeah.
Okay. So look at the info that you've been given and okay, look at yes, what they're asking you. Anything else?
Yes. For the depth of focus, is it the diameter of the PCT will always affect the depth or the thickness of the?
Now that is only going to be for us, okay, if there was one PCT. Clear?
Okay.
Right, okay. Because, okay, for your array transducers, that's okay, the shade or the size of the PCT does not change. But that was mainly going to be as, okay, the phase delay that will determine your focal depth.
Okay.
And that phase delay can change. And it continuously can change, especially as, okay, if you have set your focal depth at multiple depths. Did that make sense?
Yes, thank you.
Okay. And that's why I say is, okay, please do not confuse focal depth with depth of image. They are two different things. You could still have read a book from A to Z. But in that whole book, yes, okay, it might have been, yes, okay, the 16 chapter that captured your attention. Or that caught you. Right? So that will be your focus. You will say, well, okay, I read this book, it has 600 chapters. But chapter 30, 69, and 50, and okay, that's 120. Those were the chapters that mainly, yes, okay, just caught my attention. Or that I was really focused on. But you still read, okay, as the other, yes, okay, or the whole, yes, okay, book from A to Z. It had 300 chapters. But that was just something in those, that's okay, 2-3 chapters that, okay, has caught your attention. Which was your focus? Or because, okay, you as a sonographer say, okay, I can still just, okay, view your depth of XYZ centimeters. But I will be focusing at this depth, this depth, this depth. The benefit of OKS and array transducers are that OKS we will be able to focus at multiple depths if you want to. Just because you're using an array transducer doesn't necessarily mean that you need to focus at multiple depths. Because what if you are scanning just, okay, look for some movement, but still using an array transducer? You just want to keep a single focal point. Because multiple focal points, okay, will affect your temporal resolution. Ish,
Sir, how many questions are on the midterm? If you
I don't know.
Okay.
It's not going to be as short as your quizzes because it is a midterm. So that's all I can say.
Can we like briefly touch up on like the thickness and the propagation speed, or the thickness of the PCC and the propagation speed, how they're like related?
Did we talk about that yesterday, dear? The anniversary related.
Okay, yeah, we did, sorry.
Yeah. And you can mean, okay, just put it in that way as smuggling is okay, that the thicker the PCT, the greater the wavelength. The greater the wavelength, the lower the frequency. Anything else? So there's always just okay a cheat. Yes, ladies. Any last words of wisdom?
Are we going to have like, not labeling, but are we going to have diagrams and ask about them? Because I know that some of the questions you told us to, some of the figures you told us to know.
You can. Especially okay, if you get a question like, okay, yes, things like, okay, focal depths and things like that, right? You may get a picture.
Okay.
Right, okay. You may not get a picture where, okay, the diagram is mean is okay, just verbally explained. So that's when yes, okay, you will be reading a book or reading, okay, yes, a couple of sentences that help you picture that. Apish?
Okay.
Because, okay, when you look at the questions in your exam review, there is actually no diagrams. Okay, the picture in the back, the questions in the back of the book doesn't really have diagrams. They just give you a certain scenario and say, okay, so and so. So yes, okay, whichever. We just verbally as okay describes the scenario as okay, whatever. Well, ladies, that's okay if you have a solid grasp on your concept. You should be good. And if you don't, then okay, yes.
When you say concept, you mean like relationships and stuff?
I guess 90% of what we have been talking about in physics since day one has been relationships.
Okay.
Any last thing? Nope. Nobody wants to say anything? Okay, ladies. Pretty moody.
Oh, I have a question before you leave. So for that, before earlier you was talking about if the image is too bright or if it's too dark.
Mhm.
I know that if it's too bright, you have to adjust the output power, and if it's too dark,
Now,
you
adjust is the wrong word, my dear. You have to decrease.
decrease it.
Adjust could mean
Okay, decrease
turning in
it.
any direction, right?
And then if it's too dark, you have to increase the receiving gain first.
Yeah.
So if that's the case, how is that? That has, because I'm looking, because I remember about compensation that has nothing to do with it. Okay.
Compensation is going to be okay, increase your intensity and depth.
It's just for the depth. It's like if
Exactly. And that's
okay.
why they call it depth gain, right?
Okay.
Did that make sense?
Yes, it does. Thank you.
Okay. And what happens in the depth that, okay, as B have you choose, okay, you can say, it's okay, increase the amplification. Or increase as okay, yes, okay, the magnification of the reflections. Is that okay, as they had attenuated. So it was okay, lesser energy that will reach down to those greater depths, which of course as okay will produce relatively as okay weaker reflections, which will need an extra little push off okay as enhancement in their intensity to show us okay bright enough on the scan.
Okay. So when we see like in deeper depth, it's dark. That's when you'll compensate for it.
Yeah.
Or if it's like, okay.
But then you also have to think of that, okay, as transducers with high frequency will also have, okay, as a greater attenuation. So an option of, okay, as using a lower frequency transducer could also be the right answer. But again, yes, okay, you can only, yes, okay, you use the answers that are being given to you. Okay. Okay, girls, don't waste your time by looking at me. You have some books or you have some chapters to look at. Okay.
Thank you.
No problem, my dear. Have fun.
All right.
Okay.
Thank you.
You're welcome. Yeah. Bye-bye.